right, well, trust you did well on your exam in your last lesson. Students in here did very well, very pleased with how they did. We just finished going over some things. If you took the exam, make sure you find out what you missed on that. I'll go over that with you. For now, though, next section of your notes, finding the resultant, which again, I'll just abbreviate R, finding the resultant of skewed vectors. Now remember, what are skewed vectors, Michael?
They don't match up with any of the others.
They aren't any of the other things. So what were some of the other things that they are not?
Collinear and parallel and perpendicular.
And anti-parallel. But parallel and anti-parallel often will be collinear, right? So they're not parallel, anti-parallel, they're not collinear, they're not perpendicular, they're not nothing. Now remember, we said collinear vectors are easy because if they go in the same direction, class, you just add them and keep whatever direction you had. If they're in opposite directions, you just subtract them and keep the direction of the winner. Perpendicular vectors weren't too bad because when you drew the resultant, class, you formed specifically a right triangle. And especially for those in pre-cal, that's easy. For Kendall, it was a little newer, but she handled it well. You make the right triangle, and to find the magnitude of the resultant, class, you'd use the Pythagorean theorem. That's a P, not a R. Pythagorean theorem. And then to find the direction, the angle of however far off course the resultant was, class, we'd use the, or specifically the arctangent, right, of the opposite over the adjacent, and that would give us the direction. So that kind of fell in line with pre-cal work. Skewed vectors aren't any of these things. You'll have one vector maybe that goes like this, and then the next vector, it won't be at a right angle, but it also won't be in line. It'll be something like this. Well, if we took the same approach where we went from start to finish, just as we put tail of the second ahead of the first, we don't have a right triangle. We have something called an oblique triangle. And so in your notes, make a note that skewed vectors, when you draw them, will end up forming an oblique triangle. You'll start with the primary vector, you'll draw the secondary vector, but it won't be at a right angle. So when you draw the resultant from start to finish, you end up with this weird oblique triangle. Now I will generally designate, just using some letters, the primary vector as A, the secondary vector as B, and the resultant vector is C. Now that worked great for perpendicular vectors, didn't it? Because we could say that C squared equals A squared plus B squared and just use the Pythagorean theorem. But here the Pythagorean theorem is no help. We're going to have to use something called the Law of Cosines. Hang in there, Kendall. I'm going to catch you up. Don't worry. I'm going to use something called the Law of Cosines. Now, Kendall, flashback to your junior high days, sine, cosine, tangent, SOHCAHTOA, the cosine of any angle, we'll just call it theta, is equal to the adjacent over the hypotenuse. You don't actually have to know that yet. We'll use it a little bit later on, so it's not a problem to write it down. But if you were to take a random triangle and you were to look at one of the acute angles, the adjacent leg is right here next to the angle, and of course the hypotenuse is here across from the right angle. You take whatever length this is, let's just say it's 5 units, take whatever length this is, say it's 8 units, so the cosine of this angle theta would be 5 to 8. And that's all cosine is. For now though, you don't even need to know that much, you just need to know how to use the cosine button, which means if you knew this was, for instance, a, I don't even know, a 42-degree angle, let's just make something up. If you do a 42-degree angle, you just type in the 42 on the calculator, the cosine button, it would give you the cosine. Go ahead and give me, what is the cosine of 42 degrees anyway?
How did you do it again? So
you would just type 5 divided by 8, or excuse me, no, sorry. For the 42, just type in 42 and hit the cosine button.
0.743.
0.743, blah, blah, blah. Okay, so not bad at all there. Make sense? Okay. So here's the law of cosines, and it's going to look a lot like the Pythagorean theorem for starters. Write this in your notes. The law of cosines, which is what we use to find the magnitude of the resultant, is C squared equals A squared plus B squared. It's like, hey, that's the Pythagorean theorem. It is. But we have to account for the fact that we don't have a right angle right here. So we're going to account for the fact that this angle is not a right angle. Now, generally speaking, in a right triangle, we'll call the right angle C, so the hypotenuse can be little c. We're going to do the same here. The oblique angle, whatever angle is formed between the vectors, is going to be our angle C. And we're going to subtract twice the product of A and B times the cosine of that angle C. That's what we call the law of cosines. Once you've written it, say it with me, class. C squared equals A squared plus B squared minus 2AB times the cosine of C. You can see that's a lot to plug into the calculator. So that's one of the things we're going to work on today, is getting comfortable entering all that into the calculator. That's going to give us the magnitude of the resultant. Once you know that, well, we're going to also then need to put this into the memory of the calculator. And I believe we've worked on that before. Kendall, you good with the memory? The stow 1, stow 2, stow 3. Okay? Because we're going to turn around and use this then to find the direction. Now remember, the direction here was primary vector to resultant, where the object, bird, ship, plane, boat, whatever, was trying to go, right? How far off course did it go? And we find the angle theta right here. Well, think about it. If this is side B, then the angle would be angle B, if we wanted to think of it that way. We never had to assign letters to it necessarily. We just used Pythagorean theorem and arctangent. But the same would be true here. Here's where the whatever wanted to go. Here's where the whatever actually went. So still, however far off course, that's our theta, but it's angle capital B. To find the angle, we have to use what's called the law of sines. The law of sines. Again, Kendall, going back to your junior high days, sine so katoa is the opposite over the hypotenuse. If we had random triangle, here was my angle theta. I knew this was 8, I knew this was 5. This doesn't actually work out, by the way, mathematically. I knew this was 7. Again, that doesn't work mathematically, but if it were, we would say that the sine of theta is opposite leg over hypotenuse, or 7 to 8. More practically speaking, if I knew that this angle was, say, a 62-degree angle, I would just take the sine of 62. So on your calculator, hit the sine button, or 62 and then hit the sine button. So 62 and then hit sine.
0.8829.
0.88, so it's actually pretty close there with the 62-degree angle guess. But that's how you'd find the sine. Now, remember though, we said for this angle, we wouldn't use the tangent technically to find the angle, but rather the arctangent of the opposite over adjacent, right? Because the arctangent is what gives you an angle. If you know a 62-degree angle, you just hit the sine button to take the sine. But if I wanted to know, okay, I don't actually know this is 5, but if I knew the opposite was 7, I knew the hypotenuse was 8, and I wanted to find the angle, I could take the arc sine of both sides. So now 7 divided by 8, just like we did for arctangent, and take the arc sine, or the second function sine on the calculator. How big really was the angle? It's not 62 like I wrote, it's
61.
61. I told you it was close. It's 61.044. Ooh, almost exactly 61. Okay, so it's 61.0 blah, blah, blah degrees. So just as we take arctangent of opposite over adjacent, the arc sine is used, opposite over hypotenuse, and you just take that to find an angle. We're going to need that in what's called the law of sines class, which we'll use to find the direction. So coming back to all of you now, I know I directed a lot of attention toward Kendall because kind of catching her up on some things. The law of sines, and you two have actually seen this on some of your SAT prep and ACT prep. It's A over the sine of angle A equals side B over the sine of angle B equals side C over the sine of angle C. This one's a little easier to memorize, I think. You can just kind of see the pattern. Now, remember that the angle you'll be ultimately looking for is angle B. And so what you're going to end up doing is, instead of working with 3 ratios, you're really just going to use the last 2. Side B, which will always be your secondary vector, divided by the sine of angle B, which is always the angle you're finding, equals size C, which will be in the memory value, divided by the sine of angle C, which will be the angle between the vectors. Okay? So these are the equations we need to know. Let's say the law of sines together, class. A over the sine of A equals B over the sine of B equals C over the sine of C. The law of cosines again, class. C squared equals A squared plus B squared minus 2AB times the cosine of C. And then the law of sines again. A over the sine of A equals B over the sine of B equals C over the sine of C. Take out your books, open to page 100. Let's look at some example problems that use these two laws. And I'll get you comfortable plugging things like this in on the calculator. There's an example problem at the bottom of page 100. Go and read that for us if you would, Michael.
An airplane flying at 65 miles per hour due east encounters airstream blowing 45 miles per hour at 30 degrees north of east. Find the airplane's resultant velocity.
All right. Now, again, this is a very slow airplane. I don't know that I've ever seen an airplane fly at just 65 miles an hour, okay? I don't know if an airplane can stay in the air. I don't know. I don't know that much about aviation. Maybe that's legit. And this airstream of 45 miles per hour seems pretty strong. So it's a very slow airplane caught in a very strong wind. Does it make sense the airplane probably gets blown off course a fair bit if he doesn't compensate, which we don't even know what's going on. Okay, so here's what we're going to do. We're going to start with the primary vector. The primary vector, class, is the airplane's trying to go due east. So we'll draw a vector that goes due east. The next part's the fun part. What direction is the secondary vector, class? It is 30 degrees north of east. So here's what you're going to want to do. You don't necessarily have to do big hand gestures, but you're going to want to think hand gestures. North of east means we start where? East, and we go 30 degrees north. So we've got something that doesn't go east, class, but goes north of east at a 30-degree angle. Do you see that? We're going to start with the primary, and where you leave off the primary, that's where you will start the secondary. This was 65 miles per hour. This is 45 miles per hour. We could call this a primary vector A, secondary vector B. Make sense? And just like we would have done with the perpendicular vectors, we're going to draw a resultant from start to finish. There's my resultant, which of course would be letter C. Now, remember, for the magnitude of the resultant, which we'll always find first, we're going to use the law of cosines. We're going to say that C squared equals A squared plus B squared minus 2 times A times B times the cosine of angle C. Watch. Angle C is that angle. We don't know angle C. Oftentimes you'll have to find angle C. What is angle C, class? Careful. 150 degrees. We know that if the air were going due east also, there'd be a full 180 between them, right? They'd be collinear. But there's 30 degrees off of that, so there's a 150 degree angle. Do we see how to set up the law of cosines? Now, obviously at the end, and you, Michael, you could actually plug this in at the beginning because you have a direct entry calculator. You can put your square root symbol at the beginning. The rest of you, you're going to take this at the end. Okay? So let me show you two how to plug it in. Michael, you really can. As long as you're careful with your parentheses, you can plug it in exactly as shown. You all will plug it in almost as shown. You'll still hit, you ready? 65 squared plus 45 squared minus, now hold on, you're going to want to put parentheses around all of that. Minus, and then parenthesis, 2 times 65 times 45 times, hold on, remember you can't type cosine 150. You have to do 150 cosine. Times, we already said 150 cosine. Now close the parentheses and then hit equals. That's not your c. That's the c squared. Remember, you haven't hit the square root yet. So now you'll finish with the square root last. And how fast is that plane going, class? Good, about 100, is it it's 2 sig figs, about 110 miles per hour. All right, how many got the 106.37? All of you did, excellent, okay? That's the magnitude of the resultant, correct? But we also need to find the direction, because the plane, I mean, think about this. This airstream was kind of behind it, wasn't it? It was pushing it a little off course, but it was largely behind that plane, pushing the plane forward and slightly sideways. So it's pushed a little bit off course here. This is my angle B, this angle theta right here. To find the direction of the resultant, class, we need the law of sines. Specifically, by the way, remember I said put this in the memory, store 1 if you haven't already. You put that in the memory because we're about to use it. So coming over here, we'll say that B, well that's the 45 secondary vector, over the sine of angle B, which I do not know, that's what I'm finding, equals C, which is my memory value, over the sine of angle C, which is 150. Do you see how to plug in the numbers into the proportion before we do anything on the calculator? Now, since we're solving for B, to solve a proportion, we cross multiply. Start with the two known values. Take 45 times, again, it's 150 sine for you indirect entry people, equals, and you should be at a 22.5, correct?
Mm-hmm.
Now, what do you do with the memory 1? It gets divided out, correct? So you're going to divide, recall 1, equals, and what you see on your calculator, class, is the sine of B, 0.2115. We don't want the sine of B, we want B. I got to get rid of the sine. How do I get rid of the sine? Arc sine, second function sine. So once you got the decimal, it's going to be a weird decimal, second function sine, that's the angle. And what is the angle, class? 12.2 blah, blah, blah degrees. So we'll say the resultant is 110 miles an hour. At will round to 12 degrees. Where was the plane going, class?
It was going east.
East, but it was pushed ever so slightly to the north of east. And there's our resultant. Now, the book does it a different way. Don't worry about the way the book does it, okay? Ignore the book solution. This is the way we're going to work it. I think it's a more direct approach than the parallelogram approach that they try to set up. Questions on this? Let's do another one. We're going to do the same problem, but this time the plane is headed west. All right, so now plane is headed west. So we start with an arrow going this way. Still 65 miles per hour. The airstream, let's suppose, is still the same airstream. It's not going east, class. It's going 30 degrees to the north of east. So there's my 45 miles per hour, and it's a 30-degree north of east. Notice, that's the actual angle between the vectors, isn't it? Last time I had to say, well, if it's going this way and there's a 30-degree push that way, that gives us a 150-degree angle. Not this time. That really is the angle between the vectors. And the resultant is going to go start to finish. Do you see that the vector looks shorter this time? Why? Because the wind, while it's pushing him slightly this way, it's also largely in his face, at the nose of the plane. It's a headwind slowing him down. So we should expect a much lower resultant this time, shouldn't we? But to find the magnitude of the resultant, class, we're going to use the law of cosines. We're going to say that C equals the square root of, or C squared equals, A squared plus B squared minus 2AB times the cosine of C, which actually, class, is 30 degrees. Now remember, we're putting parentheses right after the minus sign, and we're going to need to hit equals before we take our square root. Michael, you should be able to just plug it in naturally at your seats. 65 squared plus 45 squared minus parentheses 2 times 65 times 45 times 30 cosine close parentheses equals, take the square root. He got slowed way down.
34.4.
We end up with about 34 mile per hour flight, if you can imagine a plane staying in the air going that speed. Kendall, did you get the 34.4? And Audrey got the 34.4. Now, put it in the memory. I will say this. I am a prophet, only because I've done this for 11 years now. And what will happen on a quiz at the least opportune time, one of you, I don't know which of you yet, I'm not that much of a prophet, one of you will be working a problem, and all of a sudden we will all hear you go, oh. That sound means I forgot to put it in the memory and I've got to redo the whole thing again. And it's an annoying long thing to do again. And if you forget the memory, you'll be the one going, oh. Okay? If it makes you feel better, I've done it a number of times myself at the chalkboard. So putting it in the memory. All right, once it's in the memory, we know the magnitude of the resulting class. We need to know how far off course the airplane was pushed. We need to find angle B, since we know side B, angle C, and we now know side C. In order to find the direction of the resulting class, we need the law of sines. So I'm going to use the B over sine B equals C over sine C. How would I write that, class? Over the sine of the B that I don't know equals memory 1 over, not cosine, sine of 30. Law of sines just has sine in it. Law of cosines uses cosine in it. All right, so 45, secondary vector over sine of B, which I'm finding equals the memory resultant over the sine of the 30-degree angle. Again, you're going to start with the two that you know and just multiply. 45 times the sine of 30. Then divide out the memory value, divide out recall 1, and then finish by taking the arc sine, the second function sine. How far off course? Way further off course this time, right? How far off course does this plane go? Is it? About 41 degrees off course. Did you get the 40.8? And the plane was trying to go where?
West.
But it got pushed to the north of west. And there's our answer. Make sense? Let's do the same problem again. But let's suppose this time our airplane is trying to fly south for the winter. All right? I'm kidding about the winter part. My fact checker just went off. All right, so anyway, so airplane's flying south at 65 miles per hour. Same wind, class. The wind is still blowing, not east, but 30 degrees north of east. So I like to use a dotted line to start it out and say we're going 30 degrees north of east. That's where the 45 mile per hour wind is. Do we see the primary and secondary vectors? The resultant will go start to finish. Now question, what is the angle between the vectors? 60 degrees this time. The first time I had to find the supplement. The next time it just was the 30. Now I have to find the complement. Do you see there's not a set thing you'll always do, but you do have to figure out how to find the angle, and geometry helps with that. So I need to find the resultant. I'm going to say that c squared equals
A squared.
65 squared plus 45 squared minus parenthesis 2 times cosine of 60 this time. Close the parentheses. You guys will hit equals, and then you'll take the square root. Not slowed down as bad this time. Still slowed down a little bit, but not slowed down as badly as last time, because the wind last time was in the face of the plane, or at the nose. Now, it's kind of more of a crosswind than anything else. Call it when you've got it.
58 miles per hour.
About 58 miles per hour, 57.66. And getting nods, excellent, put it into memory. And then we can say that 45 over the sine of B equals memory over the sine of 60. So we'll take 45 times the sine of 60, divide out the memory value, and then don't forget at the end you have to take the arc sine to get the angle. And what's the angle this time?
42 degrees.
A little bit further off course than last time. Around actually 43 degrees, so 42.5. This is the furthest the plane has been blown off course so far. Why? Because the wind is almost, it's not so much in its face, though it is a little bit, it's more of a crosswind, blowing it further off course than we saw last time. Remember, the plane was trying to go south, and it got pushed to the east of south. The plane was going south, but it got pushed to the east of south. Do you see how to spot the direction? Well, there's only one thing we haven't done with our plane yet, besides speed it up. Hasn't gone north yet.
Crash it.
And we don't go north. We don't go north. But anyway, we're going to in this problem. So the plane is flying north for the summer. How many have thought at times, I wish I could go north for the summer? Yeah, it's hot here. All right, so going north at 65 miles per hour. The wind class is still 30 degrees to the north of east. So watch, the wind is not east. It is 30 degrees to the north of east at 45 miles per hour. Do you see how the wind is kind of crosswind still, but slightly pushing it a little bit more ahead? So we can see this when we draw our resultant vector. The resultant is longer again. So the effect is that the air should be speeding up the plane. The wind should speed up the plane a little bit. So we should get something bigger than 65. At your seats, you do the whole process now. So our secondary vector is 30 degrees north of east still. Here's east, here's 30 degrees north of east. So we just stick it on the end of the vector.
My mind's going two ways because I'm thinking that I could just add 30 to 90.
Oh,
But-
yes, as far as the angle. Sorry, I didn't mean to go over that with
Then
you
I could,
first.
do the supplement.
What would I do? Would I do what Michael said? Would I add 30 to 90? Yeah, exactly. So what is the angle class?
120.
120. Sorry, I did mean to ask for the angle before I told you to work it. All right, how many had 120 though? You figured that out on your own? Does it make sense now? So this time I'm not finding a complement or a supplement or the angle. I'm actually adding 90 to the angle. It's different every time. So you can't just memorize, always do this. It's figure it out, think logically. Okay, now we're ready to work it on our own. Not as fast as the first time, but still pretty fast. Should have 95.78. You get that? Michael's going to get it again. He was my first. All right, so we're going to round and say 96 miles per hour. And on that cue, Michael, store 1. All right, thank you. And not as far off course this time either. Should get a 24-degree angle, 24.007. Michael's got it. Kendall's got it. And Audrey's got it. Now, how would I describe the direction? Well, where was the plane trying to go, class? North. Trying to go north. And it got pushed to the east of north. Again, the intended direction is always the last thing mentioned. And we'll tell which way off course was it going. It was going north, it was pushed to the east of north. Do we feel like we understand the 4 different ways you could use the same 2 equations? And it varies by problem. There's not a way to memorize what's what. You always use law of cosines for magnitude. You'll always use law of sines for direction. But every problem, the picture is oh so important. You'll have just one problem to do for homework this evening, and that's page 109. Page 109, problem 7. Page 109, problem 7. And we will take a look at that in our next lesson and do more practice in our next lesson with these skewed vectors. All right, you are dismissed. Have a wonderful rest of your day.